All right, in this video, I'm going to quickly go over how to solve for chi-square. Chi-square is a value that determines a set of data's statistical viability. So when you have some data and there is an expected ratio, this will let you know whether or not your data meets the expected ratio or not. If it meets the expected ratio, that's what you would expect. If it doesn't meet the expected ratio, then there's something else that is causing that change. And so a lot of time what we will say is if it meets that ratio, we'll say that any change, any difference is just random. And if it doesn't meet that ratio, then there's something else that's causing the change. It's not just random. So I'll use an example. Well, let me go through this equation first. So here's chi-square, this value. This is you're never to take the square root of this, by the way. So chi-square is the value by itself. So you never take the square root of it. You always it is what you're solving for, chi-square. All right. This means sum. And so if you have multiple things you are solving for, you're going to do this equation right here multiple times and then add all of those values together. And this O means observed. That is the data that you received. Expected is the data that you thought you should get, or the null hypothesis is another way of saying that. This is if all things being equal, this is what I think I should get. And then you're going to square that number and you're going to divide that again by the expected. And then we'll use this table in the next step. Let's go over a problem. So let's say I have a coin and I flip it 100 times. 100 times, 100 flips. What are my expected ratios? Well, I'm going to get either heads or tails, obviously. And I'm expecting to get heads and tails 50% of the time. All right, it's something we all understand and know. Well, let's say that my actual data when I did the experiment is, I'm just coming up with these numbers off the top of my head. 64 on heads and 36 on tails. Is this number close enough to the expected value for us to just say, that's just random? So that's what chi-square is going to solve for. And so I'm going to do my chi-square problem, which, again, the equation is right here. Observed minus expected over expected. And so for heads, I expect, my observed, so let me write heads here. My observed is 64. My expected is 50. And I'm going to square that, and I'm going to put that over the expected, and that is my value. All right, and so get my trusty calculator out here. That's 14 squared divided by 50, and that number is 3.92. Well, on tails, I get the same thing, basically. It's not always going to work out this way. It's just going to be different. So let's go ahead and do the math here. Expected, or my observed, was 36. My expected was 50. That's going to be negative 14, but since it's squared, it doesn't matter. And then that's same thing over 50. And so again, I'm going to get 3.92. And that's going to add together to be 7.84. And so that value is equal to that is my chi-square value. All right, so what do I do with that 7.84? Well, I'm going to take that and back into this table. And this table has a lot of information on it. For one, we are always going to look at this column, the 0.05 column. You can just ignore these other ones. They have to do with closeness of fit, and so we're always going to use 0.05. All right. On the AP exam, they're going to give you a chi-square table, and they'll probably even give you the 0.01. We're always going to use 0.05, though. And now I need to know how many degrees of freedom I have. That's what this D is, stands for degrees of freedom. All right, so how do I determine my degrees of freedom? So let me do a little illustration here. Let's say I have 3 cards here, and there are 3 of you, and I tell you, first person, pick one. First person picks this one. Second person, pick one. Second person picks this one. Does the third person have a choice? They do not have freedom of choice, right? And so how many free choices are made if there are three things? 2. The degrees of freedom are always one less than the number of items that you were solving for. And so in this case, we solved for 2 things, heads and tails, right? And so the degrees of freedom is 1. And so I'm going to take my 0.05. I'm going to take my degrees of freedom as 1. And this is my critical value right here. This is my critical value. And so I'm going to take my critical value and I'm going to compare it to my chi-square. And my critical value in this case was 3.84. And so if my critical value is greater than let me go back to, let me reverse this. If my chi-square value is greater than my critical value, then we reject the null hypothesis, which is saying this is not close enough to random for us to accept this. And so basically there's something wrong with that penny. That's the way to think about it. Maybe it's weighted a little more towards the tail side because it's causing heads to come up all the time. I don't know. And so that's what we do. If our chi-square is less than our critical value, then we accept the null hypothesis and say, yep, it's close enough to random so that this is exactly what we expect it to get. Now we're going to do an experiment in here with looking at mitosis cells, and we're going to see a slide full of cells. I don't have a picture of a slide full of cells. And you're going to count those cells and you're going to determine whether or not they're in interphase or in mitosis. And then you're going to compare that to the values that you expect. What values do we expect? Well, we expect 90% of the cells to be in interphase and 10% of the cells to be in mitosis. And so we'll do those values for the slides. We'll compare those numbers and see whether or not that hypothesis is true. This is the sort of thing that you'll do in a statistics class as well, but it's used in biology quite a bit to just determine, okay, something is off here. This isn't what we expected. And that's when you can do further experimentation to find out what is causing that change.